Oh, wait, hang on. There's one thing I forgot to do.
Just let me know when you're ready. I will.
Yeah.
Okay.
Ready.
Would you like
ready.
to start sharing your screen?
Yeah.
Or are you going to give your spiel first?
Yes, but I'm going to share screen.
Okay, great.
Different
Great.
screen.
Okay. Well, I guess we should get started. So welcome everybody to this week's session of Intercats. We've got Jules Hedges on behalf of the University and College Union, I think it's called, the UCU, who are, he's a member of the union and they're striking, and he's going to tell you why before he's going to talk about the thing that we're all here to learn about, optics, I think, and lenses and how they relate to the things we've heard about so far. So without further ado, Jules.
Thanks. So I'm very sorry to say that I'm going to spend 5 minutes of your time at the start of the talk talking about why I'm on strike, and then the remaining 50 minutes or so we'll get into the fun stuff. So I'm pushing my luck by giving this talk. Officially, I should not be giving this talk, and I agonized for about a week wondering whether to reschedule, which would have been a bit of a headache because our schedule for this for Intercats is full for about 6 months. We've got 6 months of exciting speakers coming, so I would have been putting the talk off until like July or August or something. So I decided to push my luck by speaking here on behalf of myself, basically. So I'm not representing my employer today. We are striking over 2 different disputes. The first one is over pensions, which is an extremely boring one, but kind of important. Boring but important is pension. So my pension's been cut by something like 35%. Just a crazy, like it's so much that when I retire I won't have enough money to, like, the what remains of my pension is like less than I currently pay in rent. So that's the first thing. That's yeah, boring but important financial stuff. And the significantly more interesting part of the strike is more like over the soul of higher education in the UK. Essentially, we're opposing all kinds of aspects of the marketization of higher education. We've got like shocking pay gaps for all kinds of statistics. We've got casualization, which I think of like a thing that US universities do. So these are like temporary lecturing contracts. These are a relatively new thing in the UK, and they're taking off very quickly. So we're trying to kill these off before they can really take hold. And workloads is so there's routine stories of academics working 60-hour weeks and this kind of thing, especially during COVID, with everybody moving their teaching over to online at the beginning of the pandemic. And this is a dispute that's been going on for years, since much longer than I've been in UCU. It's been essentially paused for the duration of the pandemic, and now has resumed. So today is the last day of a 7 working day strikes. We've been striking since the beginning of last week, and today is the last days. But word on the street is that our aims have not been achieved, and we're going to continue in the future. So that's the deal. So I'm here representing this stuff right now. I suspect I didn't do an extremely good job of explaining that. I haven't prepared this, and I'm not like a union rep or anything. I'm not deep in it. I'm just doing my thing. stand up for like the spirit of higher education, essentially. With that, let's get on to the good stuff. So I'm going to share this one. Okay, and yes, thanks for your clapping, those of you who are. Appreciate it. Okay, so this is our third Intercats. So for this talk, I am beginning from the assumption that everybody here knows approximately what lenses and optics are, and is at least somewhat sold on why they're interesting things that we might want to study. This is still not a research talk, as in I'm not presenting new results or my results. So it's still a kind of introductory talk, but it's getting more into the gory details. So lenses are a little bit notorious for having multiple conflicting, like the same name or very similar names for almost but not quite the same thing, and terminology that doesn't quite do an adequate job of making clear what is what. So in this talk, I'm going to try and be very clear over exactly what constructions exist, when each of them are defined, and exactly how they relate to each other. So the TLDR is that we've essentially got two classes of things. We've got a bunch of things that are basically equivalent, but they're defined in different settings, and they generally coincide when they're all defined. And then we've got another bunch of things, which is the dependent version, aka polynomial functors and natural transformations. And those are not equivalent, but they're a generalization. So I'm going to talk about also how these relate to each other. And the common theme is that basically everything is some variant of the Gonet dilemma. It's just one of those things that all of these proofs involve repeated use of Gonet dilemma. Some things I'm not going to talk about. I am not going to talk about profunctor optics for a couple of reasons. One is because Bartosz talked about it 2 weeks ago, essentially presented the proof that I would otherwise have presented. Another one is profunctor optics make my brain melt. So I'm going to talk more about things that I'm more confident talking about. And also for time, that's my backup excuse. Another thing I'm not talking about is there's a kind of separate branch of lenses or class of lenses in the category of categories, e.g. delta lenses and such things. I'm not going to be talking about those either, but I am going to be talking about lens, ordinary. Oh, and another thing I'm not talking about is the lens laws, which in fact I don't think anybody has talked about the lens laws so far. Everything I say will apply to lawless lenses, although all of the equivalences preserve the lens laws. For those of you who know what the lens laws are, all the equivalences preserve the lens laws. So if you want to do them, it's basically fine. Okay, so let's get into some stuff. So this is going to be a very kind of definition, theorem, proof style talk, because I'm going to be very precise about exactly what structure we're assuming at each stage. I want to keep chat open. Okay. Yeah, I'm not going to keep an eye on chat, so if there's important questions in chat, please yell at me. I'm happy to be heckled. If you want to ask a question, just like yell at me or something. Okay. So definition. So the basic definition of a lens works in the setting of a category with finite products. So I'm going to say let C be a category with finite products. Okay. So lens C is a category where, so objects are pairs. So you've all seen this construction 10 times now. So objects are pairs, and I'm going to call these x prime. Objects of, so a pair of objects of C, and a morphism. So I'm going to write hom of lens C, and actually I'm going to switch notation. I'm going to write these vertically to save space. I'm going to say x prime. So the hom set from x prime to y prime is going to be a pair of a lens, a C morphism from x to y, and a C morphism from x times y prime to x prime. Okay, so this is that's the key definition. And with that definition, you can define identity lenses, you can define composition of lenses, and you can prove that it's associative. So you can prove that lens C is a category. Okay. And it's maybe I should say something about what the composition looks like. So if we have some x prime to y prime, just to get some kind of vague intuition. So if we have some, I'll call this v comma u for view and update, then our composite v needs to go from x to z, so it's going to go first, v prime. It's going to be first v and then v prime, and then the composite u needs to go from x times z prime to x prime, and is going to do a thing where it copies the x, which it can do because we're in a finite product category, and it takes v of that, so we get a y, and then we take u of y and z prime to get a y prime, and then we pull out the copy of x that we were keeping in reserve, and then we apply u to x and y prime, and then we get an x prime, and then we're done. Okay, now it's worth saying something about how you do not generalize this. So it may look like if we have a category that doesn't necessarily have finite products, but only has a monoidal product, then we could just replace the times with a monoidal product, but that doesn't work. You can't define composition because we have to be able to copy x in order to define composition. And then you might wonder, well, what if we have a monoidal product with a family of copy maps, something like a copy delete category or a Markov category, which many of the most common monoidal categories have that structure. So in my PhD thesis 6 years ago, something like that, I made a fairly big whopper of an error where I incorrectly claimed that if you have a monoidal category with a family of copy and delete maps, then this definition would just work. And it turns out I was extremely mistaken, because if you do that, composition is not associative. So that's how you don't generalize lenses to a monoidal category. It just doesn't work. Okay, next definition. So this is going to be a little bit of a kind of safari. I'm going to tour definitions and then talk about how they relate to each other. So now let's see. So previously we had a finite product category. So now I'm going to completely jump. I'm going to say let C be a monoidal closed category. Then that's not very clear. This is linear lenses. It's a category where, and so morphisms of this are going to be called linear lenses. This at least is what I call them. There's no quite standard terminology for this. Everyone just says lens and assumes everyone knows what they're talking about. Where hom. So in everything I'm talking about, objects are going to be pairs. So I'll stop saying that. Within lens C from x prime to y prime. So now we have a monoidal closure. So we can define this to be a map which inputs an x and gives you back a y, and also a function object, an internal hom from y prime to x prime. Okay. And this, so if C is monoidal closed, then you can show that this is a category. And actually, this is pretty straightforward to prove that this is a category. So now here's the first kind of equivalence is when both of these are defined. So the case when both of these are defined is exactly when C is Cartesian closed. If C is Cartesian closed, then C is isomorphic to then lens C is isomorphic to lens C. Okay. So let's see the proof. Should I start a new page for this? I guess digital paper is free, although I might want to keep the definition on the screen. Okay. No, I don't think I'm going to fit it. So maybe you can sort of guess how this is going to go. So the equivalence is identity on objects, and in general, all of these equivalences are going to be identity on objects. So all we're actually doing is exhibiting bijections between the hom sets. So our homs in lens are going to be from lens C from x prime. Oh God, what am I doing? To y prime is by definition this times this. And now, because C is Cartesian closed, we can transmute this. So this is hom C, that's y times hom C x, and then hom object from this. And then because hom preserves limits. So here is where we use that it's closed. Here is where we use that it's Cartesian, right? So this bit would work for a monoidal closed category. This bit you need that your monoidal product is actually a product, is a limit. So this is hom C x y times. Okay. All right. So that's great. So we've got a thing that works in final product categories, a thing that works in monoidal closed categories, and when you're Cartesian closed, they coincide. So that's good because Cartesian is a common structure, monoidal closed is a common structure, jobs are done. Okay. So now we can strictly generalize it. So the definition of optics kind of strictly generalizes this. So C be just a monoidal category, then optic C is the category where Again, objects are pairs. So this is going to be the coend definition of optics. Again, optic is another heavily abused word because optic can mean a coend optic, but it might also be profunctor optic or van Lahoven optic. Okay, so I'm going to say hom optic C x prime to y prime, and now this is coend over say A in C of hom C x a tensor y times hom C a tensor y prime x prime. So as a reminder, this is a coend in set because this hom set is a set. So that is to say, coend is set, you can give it its concrete characterization, it's a quotient of a disjoint union. So these things are a triple consisting of an A together with a morphism like this, together with a morphism like this, quotiented out by an equivalence relation. Okay. Now, okay. So now's where things are going to get tricky. So here's our proposition. If C is Cartesian monoidal, then lens C is isomorphic to optic C. Okay, so I'm going to start a new page for the proof again. So our hom sets in optic C is this thing. So it's x a times y times hom C a times y prime x prime. So notice we now have, so notice in this definition we have, this is the monoidal product in C, this is the Cartesian product in set. So now we have Cartesian product in C, Cartesian product in set. These are not the same thing. So what can we do with this? Well, hom preserves limits. So we can say like a map into a product is a pair of maps. So hom preserves limits. So now we have integral a and c, hom C x a times hom C x y times hom C a times y prime x prime. And now here's the magic trick. Now we have the thing called the ninja-Yone dilemma. Which says that if a coend is like an integral, then hom behaves like a Dirac delta. So if you have coend over some stuff where one of them is a hom functor, you can just evaluate, so you can substitute this x for everywhere that a appears. So by the Yone dilemma, this thing, and then the coend vanishes. So this is hom y times hom C x times y prime x prime, which is the hom in lens. So this is probably the most important proof, I guess, in this talk. We move between these two forms all the time. I think it might be worth drawing a picture of this as well. I'm I'm presenting the Unidal lemma in this form as basically a black box. It's a thing that I'm assuming is true. I'm not going to attempt to prove it. So the kind of picture version is a lens looks like this: x prime, y prime, and by picture I mean string diagram. So lenses look like this. Optics look like this. And then this is that's what we call the residual, the type that's bound in the coend. So the equivalence going from lenses to optics is you just pretend that V together with this copy map becomes the new V. Now going the other way, turning an optic into a lens is kind of tricky. So we can kind of use the fact that in a Cartesian world, doing V once is kind of like copying the input and doing V twice. And then in the first one, we're going to use the first output and delete the second output. And we're going to do it like this. And then, am I doing this right? Yes. And then we move this V to become part of U. So we kind of slide this down here. I'm not intending these pictures to be informal. I'm intending to give a different perspective where this is a kind of completely by magic algebraic proof, and then this is a proof in scare quotes by kind of eyeballing pictures and moving diagrams around, and they do agree with each other.
What are the letters on the boxes? Are they all V? Are they U? Or
oh, sorry, yeah. This is a V. So in general, the ones with a flick are U, and the ones without are V. So V, U, V, V, U. Hopefully that's clear. Oh, there's lots of stuff happening in the chat. Yeah, okay. Questions are being answered, okay. All right. Okay. So here's another proposition. If C is, that's kind of the obvious missing one that I haven't said yet. The combination of things that we haven't covered is if C is monoidal closed, then optic C is equivalent isomorphic to linear lenses. So how are we going to do this? It's going to be kind of, it's going to look the same as this, but we're going to do a completely different sequence of steps. So this is integral A, C, X, A tensor Y times on C, A tensor Y prime, X prime. Okay, so what can we do here? Well, because this is monoidal closed, we can move this around. what am I doing? A tensor y times hum c a to internal hum y prime x prime. And now again, we have a coend being evaluated as a hum functor. So we can just substitute this thing everywhere that a appears. So this is hum c x y prime comma x prime tensor y. And here is where I discover that either I have to say that C is not just monoidal but commutative, symmetric monoidal, or I define linear lenses backwards. Like 99% of the time I live in a symmetric monoidal world, so I don't worry too much about that kind of thing. But if you want to be minimal with your assumptions, then you have to be careful what order things happen in. And apparently these need to be the other way around to work, or you define optics the other way around. There are multiple different equivalent ways of making things line up. If you're symmetric monoidal, it doesn't matter. You just swap them around. Okay. Oh yeah, of course. Hum, then lens. See. So what this means is, so here's the kind of the kicker. In a general monoidal category, you can define, and I mean, a monoidal category is an extremely minimal assumption, right? There's a lot of monoidal categories. In a general monoidal category, you can define optics, but it involves this kind of scary coend. And actually, then you do have to, if you're inclined to worrying about set theoretic foundations, you do have to worry about whether this coend actually exists. This is not automatic, because this is generally a proper class sized colimit in set. If your monoidal category happens to be Cartesian, then you have an equivalent form where you can eliminate the coend. If your monoidal category happens to be closed, you have a different equivalent formulation where you can eliminate the coend. If your monoidal category happens to be Cartesian closed, you can do this in multiple different ways, and they all coincide. So you could say something like, if C is Cartesian closed, so here's a kind of trivial corollary. If C is Cartesian closed, then well, all these things coincide. What I want to say. Yeah. So of course, Cartesian closed is the nicest possible setting. In practice, there's kind of two different schools of thought on this. As an applied category theorist, I personally like to work with the structure that kind of nature gives me, which means I really like coend optics. I'm often working in categories that are just merely monoidal with no other structure. So for example, in Bayesian open games, we work mainly in the Kleisli category of a probability monad, kind of typical Markov category. And these are typically, I mean, they're never Cartesian, otherwise your probability degenerates. And they're, I think, typically not monoidal closed either. So those are kind of categories that appear in the wild in my work, which are kind of merely monoidal as their natural structure. But it's nice to know that in kind of nicer categories, more structured categories, nicer is a bit of a subjective word, but in more structured categories, you get kind of multiple different representations that coincide. Okay. So in summary, say if I want to put all of this on one slide, we have monoidal, we have Cartesian, we have monoidal closed, and then we have Cartesian closed. So here we have optics. Here we have what I called just lenses, so concrete lenses, I should call them. That's their more specific name, concrete lenses. The pair of maps one, and here we have linear lenses. And then in Cartesian closed world, we don't have a specific form that's specialized to that, but both of these are defined and equivalent. Okay. So that's the summary of like the first half. Okay.
Sorry,
let's
Jules,
talk. Yep.
maybe it'd be worth saying, so which one's a generalization? I mean, I know you said it, but just to summarize, you drew it, but you didn't quite say that they all
optics,
agree.
right? So
whenever they agree, yeah.
Right. So going downwards is more specialized. So every monoidal category is Cartesian. Every Cartesian category is monoidal. Every Cartesian closed category is Cartesian. So as you go down, you get less examples. So optics here is the most general. It's defined on the most categories. These remain defined as you go down.
And they all agree up at the top.
And they all agree when they're all defined. So each thing is defined in where it is and everywhere below it. Okay. So, right. And there's also Van Lahoven lenses and profunctor lenses, which I'm not going to talk about again, because Bartosz understands it better than me and he already did it. Okay. So now, in the second half, 1/3, it's fine. I'm going to talk about the kind of dependently typed version. So things are going to get briefly more hand wavy because at some point we have to kind of guess a definition. So let's think about set for a minute. So we have, I'll switch to capital letters for reasons, because I'm going to write some elements. So a lens like this is a function. So we have set, and then we have a function from x to y and a function x times y prime to x prime. There is a kind of obvious, in scare quotes, generalization of this that you can do in set, which is to allow things to depend on other things. So one thing you can do is to say that x prime depends on x. So I'm being informal here. I'm saying that so x prime here, if I was a dependent type theorist, I'd say that x prime is a function from x to set. And same, I can make y prime depend on y. Now, so what I can do here, so now if I wanted to generalize u, what I would have to say is that because y prime and x prime are now indexed things, so I just have to say u is that takes an x, and now I'm going to have to name the input times y prime, and now I have to say what our index is, and our index is going to be v of x, right? We have to give it a y. So we're going to take some element of y prime that's over v of x. That's the only y we have kind of in scope. I'm talking like a functional programmer here. Now we're going to get back an x prime over x. If I wanted to write this in kind of more traditional mathematical notation, u would be an element of this tuple, say that for all x in x, we get a function from y prime of v of x to x prime of x. So this was all in set. So there are a few different ways of kind of talking about this in category theory. And what I'm going to do is I'm going to go to the most general possible definition and then instantiate it later to more specific things. And the most general possible definition is a thing that David wrote down called F-lenses. So the starting data we have for an F-lens is a thing called an indexed category. So we have definition, let F be a functor. Okay, let C be a category. So C is now just a mere category. And F from C op to cat be an indexed category. So an indexed category is a functor from C op to cat. Then F-lens is a category where, so the objects are going to be pairs X prime, where X is going to be an object of C, and now X prime. So we have, if we have an object of C, we can hit it with F and we can get F of X, which is a category. It's object of cat is a category. So X prime is going to be an object of that category. And then a morphism. So hom of F-lens from X prime to Y prime is going to consist of a have I screwed this up? I may have screwed this definition up. Let's see how this goes. We're going to need a morphism from X to Y in C, and then we're going to need a family of morphisms. So we're going to need to go from, hang on, hom C, and then we're going to need to do hom in F of X. Yeah, this should work. Oh yeah, this should work. And we're going to land in X prime, which is indeed an object of F of X. And the source is going to be F of, so it's going to be, I need to name this thing. F of V of Y prime. Okay, hopefully I have got my variances correct. So because V goes from X to Y, so an F is contravariant, so F of V is a functor from F of Y to F of X, which means because Y prime is an object of F of Y, so F of V of Y prime is an object of F of X. There we go. So I did get it right. If I wanted to write this in proper notation, I'd say that this is an element of the disjoint unions sigma V in hom C X Y, hom F of X from F of B of Y prime to X prime. Okay. Okay, so this is a huge generalization. Let's see. Here's a proposition which I'm not going to prove. Let C be a finite, C be a finite product category. and let f from C up to cat be given by this formula. F of x is, so if C is a finite product category, then for every object you have an x times blank comonad, and we're going to take the co-Kleisli category of this comonad, that's a category, and then we're going to take up. Then f lens is lens C. Okay, so that's the kind of link from the first half to the second half. This is the appropriate definition of an index category that gives you back non-dependent lenses. Okay. Now let's do something more interesting. So let C be a category with pullbacks. So now we have a functor f from C up to cat given by f of x is C sliced over x. So you need pullbacks in order that this thing is a functor, because this thing acts on morphisms by pullback. So I realize I don't have, I'm a little bit short of time than I hoped I would be. I'm going to probably cut off this bit of the story and say that in this case, F lens is a very interesting category of dependent lenses. In this case, an object of F lens is x in C, and then an object of C sliced over x, which is exactly a morphism whose codomain is x. So objects in this category are morphisms in C. If you work it out, okay, I'll give you the punchline. This is a construction that David showed me a few years ago. If you work out what you do with it, if you kind of work out what F lens is here, then your objects look like this, and a morphism ends up looking like a V here, and then here you take a pullback x times y prime pullback over y, you get a projection here, and then so you get a projection here, but the other piece of data is a U here. It's a factoring of the projection through this morphism. Okay. And then this thing composes by like extremely general abstract nonsense where y times z over z prime, and then the pullback of this thing ends up being this. The composite ends up being this pullback, and everything is wonderful and magic and kind of difficult to work out. I want to say a different version, which is simpler. Let f from let C be a category, let f from set up to cat be given by f of I is C to the I. So as is to say, I many copies of C. That you can also see this is the functor category from I to C, where I is a discrete category, if you like. So let's work out F lenses for this thing. So F lens for this thing is, so objects are I and then a I indexed family of objects in C. And then a morphism I guess I'm going to use capital letters for my objects from now on. That's going to be unnecessarily confusing. So I and J are sets, Xi and Yj are objects or families of objects. So this thing is going to be a function from I to J, and then a morphism in C to the I from Y of V of blank to X of blank, which morphisms in this category are I indexed tuples of morphisms. So this is to say for all I and I, it's a morphism in just C from Y of V of I to X of I. And now maybe this is starting to look familiar from the kind of naive made-up hand wave definition of dependent lenses we had earlier. I guess maybe I never called them dependent lenses, but they're lenses where you stick dependent types everywhere. Okay. Now, here's the kind of magic proposition, is that F lens for this is equivalent to what I'm going to temporarily call poly, which is the full subcategory of functors from C to set, which are spanned by coproducts of representables. So polynomial functors from C to set. So this is, I'm kind of cheating a bit to make the maths easier. Usually you would do this either where C itself is set, so these are now polynomial endofunctors on set, or you do it in the slice category version where everything is defined by pullbacks, and that gets kind of tricky, and you need it to be locally Cartesian closed for the proof to work. So you're kind of deep into categorical logic, semantics of type theory kind of stuff at that point. So let's look at the proof of this. And I'm going to, I guess I'll go to the hour. I was hoping to finish early, but I want to show this proof. Which way around shall I go? Yeah, I guess I should go this way around because it's easier. Unada is easier when you use this as a reduction than when you go backwards. When you do Unada backwards, it looks like pulling a rabbit out of a hat. So that's to say a coproduct of which way around is it? There we go. So this equivalence is not identity on objects, but the equivalence on objects is going to look like this. We kind of transmute this set index family of objects into this set indexed coproduct of representable functors. Okay. So this thing is a functor from C to set. This thing is a functor from C to set. So this is the set of natural transformations. This thing is still a coproduct. So so here it's hom transmutes limits into colimits. So that's just to say a map out of a coproduct is going to be a
Sorry,
product
the
of
F
maps.
In this proposition, which functor is F?
F, sorry, which functor is F?
Yes.
F here is this one. It goes from set op to cat,
Okay.
and it
thanks.
gives you powers, set index powers of a fixed category. Okay, and now this is now in a form where you can apply usual Unida. This is now C from set from I've screwed things up. What am I doing? Right. Yes, Unida says J in J. So this thing becomes the new thing, and we stick this X in here. C, Y, J, X, I. And then we have one more step. If we have a pi sigma, we can turn it into a sigma pi. So this thing is, so that is to say, this is constructive axiom of choice. If for all I we have a J, then we have a function from I to J such that for all I we have, and then J becomes f of I. So C X sub V of I, sorry, Y sub V of I, which, as proved earlier, is of F lens from I X I to J Y J, and that's the end. So well done for keeping up. This was an extremely non-conceptual talk. This is a talk of all of the proofs that everyone has to suffer from to understand how lenses really work and kind of an operational level. So I need to leave strictly by about 5 past. So I'm afraid I can't stick around for a super long time.
Okay, well, let's all thank Jules. Thanks, Jules.
Thanks, Jules. I actually understood all of that, which is very rare for a talk.
Amazing.
It sounds like great. Yeah, so it sounds like Jules doesn't have much time for questions, but if someone wants to raise their hand or just unmute, feel free.
And if there's lots of questions, then I'm happy for you to write to me or on Zulip or by email or whatever.
Looks like Jacques has a question.
Yeah, so what about the laws, the lens laws? What happened through all of this?
It's a lens law in itself that everyone has to ask a question about the lens laws. So the answer is, so because I'm defining these categories where you have kind of freely moving pairs, the lens laws don't even type check. So the easy way to do the lens laws is to cut down to the subcategory where you have where the two objects are the same, and then you can impose the lens laws. And the answer is that if you do that, then all of the equivalences in the first part preserve the lens laws, and I think they preserve the lens laws even individually. For dependent lenses, I actually don't know what the lens laws should even say. So the answer is it's a bit complicated. I know there's a bit of conflict over whether lenses without the lens laws even deserve the name. So I've built my entire career on doing shenanigans with lenses that don't satisfy the lens laws, as in like the lens laws are just false, but everything else is, they compose like lenses. So I say, like, this is my take, is like, if it walks like a duck and composes like a duck, then you should call it a duck. But I know there's some conflict over this point.
I think that's good since you're low on time. If that's okay, we can move on to the next question. Matthew?
Hi, Jules. Thanks for a lovely talk. I thought it was very clear and easy to follow. I have a question about, so the stuff you were doing at the end with these dependent lenses, I wonder whether you've made much progress in doing this in the monoidal setting rather than the cartesian setting?
Yeah, so part of, so the answer is yes. And part of the purpose of this talk was to lay a certain amount of groundwork for some future talks by my colleagues here in Strathclyde who are going to talk about the details of that. The details are very, very complicated, it turns out, at least by my standards. You need some kind of serious category theory. Bartosz, I should say Bartosz has also made a fair amount of progress on dependent optics as well.
Okay.
So the answer is yes, but I've intentionally not said anything about it.
Perhaps we could talk offline and
yeah,
I don't know, but yeah, cool. Thanks.
Oh, we have a right. We have an archive preprint. Let's see if I can find it. This is more like a preprint that says we've proved some stuff that doesn't actually contain half of the proofs. But I guess now's a good time to. And we call them fiber optics, which is Bruno's name, which is a good name. Yeah.
Okay, well, yeah, so that won't show up for people on the YouTube, but it looks like it's archive 2112. Yeah, maybe you could write it in the remarkable if you want.
Or
great. Any other questions for Jules before we close the live stream?
Yeah, I'd probably have time for like one more question, Max.
Well, in that case, let's thank Jules again. Thanks, Jules.
Mm-hmm. Who's our next speaker? I actually don't remember who's our next speaker.